So here we have our bus. We have our two 8-bit registers. We'll have another one when it's all said and done. And then we have connections from our bus and to our bus, controlled by our load, enable, as well as clock inputs. So the way this is going to work is you'll bring load high and you can read from your bus. You'll bring enable high and you can write to your bus, or rather input and output. And then this will all be synchronized by the rise and edge of our clock signal here. So this will make sure everything kind of works in sync. So what a bus is a bus provides as you can see, provides communication between components of our computer. So everything is kind of connected to our bus. That's how we can get information from our A register to our B register and so on. And the reason we have a load and an enable signal, is because we may not want to input on every register at the same time, because we may already have data in that register that we like or that we need. And we may not want to output from every register onto our bus at the same time. So taking a closer look at our registers, what we can see is this section here. So minus everything on the left side is just an SR latch. And we've worked a lot with SR latches in our first few videos. That included our clock module, whether it was astable, monostable, or bistable. And we know that an SR latch allows us to store data, whether it's a 0 or 1, whether it's on or off. And that just kind of lets us know what a register is and how it works, right? Because what a register does is it stores, like fast storage or fast memory. It stores data that the CPU is currently using or computing or whatever the case may be. It kind of stores that data for the CPU. So just the fact that we have an SR latch, it's just a good thing. It's it should be connections being made is all I'm trying to say. So the way an SR latch works is it could either be on or it could be off, right? These are two NOR gates. The way NOR gates work is basically a NOR gate is the opposite of an OR gate. So if I have two zeros here at both of our inputs of our NOR gate, usually with the OR gate, it would be a 0 for an output, but instead we'll get a 1. If I have a 1 and a 0 here or a 1 and 0 here, usually with an OR gate, it will be a 1 because either or could be 1, but with the NOR gate, it's the opposite. So it'll be a 0 out. And if I have two 1s, it'll also be a 0 out. So the way this works is if we were just going to look at the SR latch. So let's just kind of disqualify everything to the left side of my pointer here. What would happen is we would say we apply 2 zeros to both of the inputs of our NOR gate. So it'll be here, here, as well as here. And what's going to happen is 1 is going to power on first. So say our 2 zeros reach here first, get a 1 out, and we have a 1 here. That means this powered on first. And it'll send a 1 to this input, and this will be a 1 and a 0, which is a 0 out. So that'll be considered on because our Q output is a 1. So that will be considered, our SR latch will be considered on. We'll have a 1 latched in there. So what's going to happen, or if you want to kind of change that value, what you can do is you can add a 1 here. And what's going to happen is you'll have a 1 and a 0, which is a 0 output because we have the NOR gate. That 0 output will send a 0 here because it's connected to this input is connected to our output. It'll be a 0 and a 0, and then 0, 0 is 1 because of our NOR gate. So now we can remove our pencil, or I'm sorry, our pointer. And what we have here now is we have that same SR latch, but now it latches based off of input data, as well as it's synchronized to our clock. So let's kind of talk about how this works. So we get a 1 here. This is an inverter, And we know that if we get a 1 inside of our inverter, we'll get the opposite. It will be a 0. If we had a 0 here, it'll be a 1. So we have a 1, inverter, 0. Our AND gate, we need 2 1s. We can think of it as both. So because it's a 0, it really doesn't matter what the clock signal is. We'll get a 0 out anyway. And we come here, we have a 1. So whenever we push our clock, we'll get a 1 out. And we'll get a 1 here to our NOR gate. And this will be a 0. And a 1 and a 0, because of our NOR gate, like we already said, is a 0. So that's good. And then what's going to happen is we already have a 0 here. This is a 0. So it'll be 0, 0. This will be 1. And we'll have it on. So if we have a 1 coming in, we'll have a 1 going out. So now, as you guys can see, it says edge detector circuit. The main difference between a D flip-flop and a D latch is the fact that here, this will be synchronized to our clock signal, while our D latch will be synchronized to an enable signal. So all the clock signal does, as opposed to an enable signal, especially on the rising edge of our clock signal, is it just allows everything to kind of happen in sync. As soon as we press that clock, as soon as it goes high, we'll have our computer or we'll have our registers taking in data or outputting data or whatever the case may be. So I was watching Ben Eater's video, and what he did is he kind of created an edge detector circuit here. And the way this will work is you have our clock signal here. So whenever we push our clock signal, or whenever if it's on the A stable, it'll just be beeping or bouncing on and off by itself. It'll kind of go and it'll go into here. And what's going to happen is, as your capacitor begins to charge, because what's happening is your capacitor is going to charge up to the voltage of your power source. So this just allows us to, everything that we're going to do, whether it be load or whether it be output, is going to happen within this time of it shooting up to the full however many voltage or whatever the case is on the power source, and then kind of coming down. We may already have data in the certain register that we need. So because of that, we've added a few extra things. This is our D flip-flop here. This is our D flip-flop. So as you can see, we have an extra inverter. We have 2 extra AND gates, and then an OR gate here. And what this does is it allows us to kind of incorporate, because we already had data, but it allows us to incorporate our load signal. And now we can decide, okay, do we want to load the same data that was already there? Do we need that data? Or do we want to load different data and forget about the data that we already had inside of our D flip-flop? So the way this works is, if you have a 0 here, it'll be a 0 here at our AND gate. So it really wouldn't matter what our data was, because a 0 and whatever else is still a 0. And what we'll end up having is a 1 so a 0 here outside of our inverter is a 1, because the inverter just changes the value. And then this takes the input of the other input of our AND gate is just the output of our D flip-flop. So if our D flip-flop output was, say, X, if we called it X, whatever, because this is a 1 from our inverter, basically the output of our AND gate will be whatever X is. And then what will happen is we'll get here to our OR gate, and this is already a 0, as we already know, because our load is low. Whatever we get out of our OR gate will be whatever X is from here. So if X is a 1, then we'll get a 1 through here, and it'll feed through here, and then it'll kind of go back if X was a 1, or if X was a 0, we would get a 0 out. But we would get the same output. Now, if load was high, if load was 1, load going through our inverter, 1 would be a 0. So it really wouldn't even matter what we already previously had stored, but it will be a 1 here. So if our data is a 1, what's going to happen is it'll come through our OR gate. and it'll want to be latched. And if our data is a 0, a 1 and a 0 is a 0, and we'll get a 0 out. So if put simply, if load is low, we'll input the same data. And if load is high, we'll input whatever the data is on our bus. So that's how we load data onto our bus. But we can also talk about how we enable data to our bus, which is just as important, because like I said, we don't want a bunch of different registers or a bunch of different components loading data on our bus at the same time. So to do that, what we can use is a buffer. And more specifically, we can use a tri-state buffer. And what the tri-state buffer is going to do is it's going to allow us to have that enable signal so that even though we're getting an input, we don't necessarily have to output if we don't want to. Because what's going to happen is well, number one, the reason it's called a tri-state buffer is because you have 3 options. You can have 0, you can have 1, or you can have unconnected. So say, for example, we have a value stored inside of our enable, and we don't really want to output our enable to our bus because we're already outputting or enabling our B to our bus, and we don't want to have 2 different values in our bus. Say if our B value is all 1s, so it's 1 here, all on our register, or I'm sorry, all on our bus. And then say our A value is all 0s. Well, what happened is the ones that are coming from our B register would just kind of short to our A register because they're all 0s and it's sinking current into it. So instead of that, what we can do, or which would be a lot better, is we could just have it to the point where it's unconnected or where it's not connected. Because like I said, a 0 would just be a value of 0. So a tri-state buffer can be used when we want to connect multiple devices to a single device, multiple devices being our registers and our single device being our bus at the same time. So this was Ben's example. So we can think of it as our input coming in. Our input is either high or low, but we don't necessarily have to enable that input and send it to our output. So as you can see, we have a switch here, and we can either open or close this switch. So we can either output a 0, we can either output a 1, or we can output nothing, which is, we may need to do that. So this corresponds to our 74 LS245 IC. It's a bus transceiver, so it transmits and receives. And what we're going to have here is we're going to have the chip that this is kind of just like what this is a representation of that IC, of what's going on inside of our IC. And the way this works is we have an enable signal, like I already said. So if enable is high, this one is inverted, so it'll be low. And our buffers here, they won't output. They will just kind of be, it would look like this, which is unconnected or open. And then say if our enable is low, it's inverted, so it will be high. And then we can think of it as this one being closed, and it can output, whether that output be a 0 or a 1. That's why it's called tri-state, because you have 0, 1, or not connected, I guess you can say. And then we have our direction here, which we're only going to be outputting to our bus from our transceiver. So, honestly, it really wouldn't matter. So with that being said, that's the end of this video. This one spoke more about just the logic and the theory behind our registers. And in our next video, we'll go ahead and talk about how to build and how to test those registers.